So again, all of these incoming messages are multiplied by this indicator S, and the sum ends up looking fairly Gaussian. Now, here's the other key observation. It doesn't really matter what the density is. Once we end up as Gaussian, we only have two parameters, which are mean and variance. And in particular, in LDPC decoding, it turns out that the variance is a function of the mean. So this is well known if you know anything about exit charts. So all we really care about is the expected value of this sum. And I'm representing that here. What's more, okay, S is a random variable. It's the random selection of bits by relays. And Y is a random variable. That's the channel observation. But clearly these must be independent. So therefore I can divide up this expectation like this, just multiplicatively. Furthermore, expectation of SI, well, SI is a Bernoulli random variable. So what's the expectation of a Bernoulli random variable? It's just the probability that it's 1. And in particular, this PI is the selection fraction. That's the fraction that each relay is contributing. That's the fraction that each relay has agreed to participate. And so therefore, that's what we're trying to optimize. Now, under LDPC decoding, this has to be greater than some threshold. Doesn't matter what that is for now, but just bear in mind, that's a constraint. In order for this procedure to be successful, it has to be greater than some real value, which is specified somewhere else. So, this is a constraint that is linear in the selection coefficients. What's more, if you think about how energy is expended here, energy per bit per relay is present here. Clearly, the amount of energy that's expended is proportional. To this selection coefficient right here. So, in other words, the constraint is linear in the selection coefficient. The energy that's consumed is linear in the selection coefficient, and therefore, what do we have? We have a linear program. So this is a situation in which here are the constraints, here's the objective, and all we have to do is throw it into LinProg and MATLAB or whatever you like, and solve it. So there it is. It's a very based on the properties of LDPC decoding and the central limit theorem. Basically, we have a very nice, very general way to optimize these fractions. What's more, we can add other constraints as long as they're linear. In particular, if each relay is only willing to participate, let's say a fraction of 0.1, we can add those constraints. We can add for each relay any kind of maximizing constraint that we like. Now, the reason why we did this is because linear programming gives you low complexity. It's a low complexity way to optimize for lots and lots of relays. So as an example, we did the following. We took demodulated forward one source with 2 relays and 50 relays. So we wanted to demonstrate that this works with a large number of relays. For 2 relays, all of the links we said had an SNR of minus 1.5 dB. For 50, we said minus 10. The reason why we chose those values is because all the links have the same SNR. It turns out that the optimized fractions on all the links are all the same. And in fact, in these 2 cases, they're equal. So we picked this particular toy example just because obviously it's very hard to visualize and even hard to generate realistic scenarios when you have something like 50 relays. So we just wanted something to indicate how this is working. Now we've made some simplifying assumptions going along here that for one thing, things are Gaussian, that things combine in the ways that we thought they would. And the result we have suggests, indeed, that our approximations are valid. So this performs exactly the way we thought it would. We would expect the threshold, so this is error rate versus fraction along the x-axis, so we would expect the threshold to occur here. The optimization routine told us that we would expect successful decoding when the fraction was right about here at 0.2926. So we see that the waterfalls actually begin there. Also, we see, as expected, the results are better for 50 relays than for 2, probably because the Gaussian approximation is a little better there. I'd just like to comment, we have run simulations, and they're in the paper, for larger numbers of relays where the SNRs are different. As you might expect, quite often, the solution is selection. So the relays will tend to select particular relays and ignore others. Although that's not always true. Sometimes the linear program will come up with solutions that only partially select some relays and partially select others. So The takeaway message here is that there's good agreement between the optimization results and the simulation. So this concludes my talk. If you'd like to hear more about fractional cooperation or any of our other work, here's my contact information, and I'd love to hear from you. Thank you very much.
Thank you. Questions for Andrew?
So when you say fractional cooperation, do you mean the fraction of the packet that's being picked up, the fraction of the battery power, or are they the same?
The question is, what do I mean by fraction? I mean basically the fraction of the data that's being relayed. So in other words, the fraction of a particular packet that's being retransmitted, or more generally, you could think of it as instead of those blue squares that I showed you, instead of those being bits, those could themselves be fractions. So these could be the fraction of packets that's being retransmitted.
And is the energy expanded for this somehow? Does it have to be linear, or could you handle some of it?
So we assume that, that's an excellent question. So we assume that the only source of energy expenditure here is in the transmitter. In other words, that there's no cost to reception. So that's not completely true, but if there is cost to reception, then that would, I don't think it would end up being nonlinear. It might be a constant offset or something like that.
Okay, thank you again.